All right, so having done that nature of scientific inquiry, is going to be a little easier to explain this coming theory that we use for the formation of the Earth. So here we're going to go through the most widely accepted views on the origin of our solar system. The theory described here represents the most consistent set of ideas that we have to explain what we know of the solar system today. Okay? So about 13.7 billion years ago is when our scenario begins with the Big Bang, which was an incredibly large explosion of all space and matter in one tiny instant. So all space and matter went from tiny to huge dimensions instantly, just very fast. As the universe began to expand, subatomic particles condensed to form hydrogen and helium gas, which later cooled and clumped to form the first stars and galaxies. The process of formation of different elements is actually very cool, but basically the cooling and the clumping of these subatomic particles created heavier and denser atoms throughout the process. So this is officially called nuclear fusion. It occurs within stars, and if you're curious, I'd encourage you to look a little bit more into it. So one of the galaxies that was formed through this process was our Milky Way, which is where we're at right now. And within it is our solar system. So as you may know, there are many, many, many stars in a galaxy. Our star, being the Sun, is the main ruling star over our solar system. In our own solar system, we actually have 8 planets, hopefully you would know that, which revolve at different speeds around the Sun. Not just at different speeds, but also some of them at different angles, and the orbit sizes vary as well. Their relationship to the Sun, along with their specific formation from the elements that were at hand, makes each of these 8 planets very unique from the others. So many of the planets, for example, have moons, which in turn revolve around them, and within them revolve around and the planets themselves revolve around the Sun. So we have a revolving moon around the planet, and the planet itself revolving around the Sun. It's a pretty cool system, that's for sure. So from the specific orderly nature of our solar system, we now know that all of the planets formed more or less at the same time and from the same primordial materials as the Sun did. So the theory which explains the evolution into our solar system today, the solar system bodies that we have today, from an enormous rotating cloud, if you would, is called the nebular theory. And again, here I just want to highlight that the theories, as we saw in the previous slide, the way we're speaking of it scientifically, is more than simply just a made-up kind of hypothesis. So many times we refer to as theories in colloquial speech as what scientific community refers to as a hypothesis. So theories, remember, are going to be hypotheses that have been tested out many times and tested out pretty much right based on observable occurrences in the natural world. Okay, so the theory of the nebular theory is what helped us kind of determine how the materials that formed our solar system went from this gigantic, enormous rotating cloud into the different bodies that we have in the solar system, those being the Sun, the planets, the moons, the asteroids, and whatnot. The nebular theory. So we had this solar nebula, which is basically a giant rotating cloud that formed from the rotation of particles. And something, we're not very sure what, caused this nebula to start collapsing in response to its own gravitation. So this something could have been perhaps a shock wave from a supernova explosion far away, but it's not a certainty. So the particles that were within this rotating cloud continued to collide to build up mass, and with mass buildup, it increased their gravity, basically. So hence they became a positive feedback loop. So more collision, more mass building, and more or a greater increase in gravity. So it became a fast spinning disk, if you would. So this made it into a disk. From what was originally a large rotating cloud, it became a disk. So you can imagine, kind of as a clarifying factor, a speed skater. So a speed skater, when they're trying to gather all the speed, they also gather their mass together. So they kind of huddle and they make a little ball, if you would, as they're skating. If the speed skater was to skate with their arms wide open and facing the incoming area where they're skating, that would not help them go faster. So when they gather their mass, they tend to go faster, which is the same idea of what happened with these particles within the solar nebula. So most of the matter within the disk ended up in the center of the nebula itself, which was no longer a nebula, more like a disk, making this matter within the center of the disk the protosun. So near this protosun, the temperatures were very high due to the gravitational energy of the infalling matter, so the matter that was coming closer to it. So the temperatures were high enough for dust grains to actually evaporate. However, far away from the center, the temperatures remained super low, at about negative 200 degrees Celsius. So closer to the middle of that disk, temperatures were very high, making dust grains being able to evaporate. But far away from that middle of the disk, temperatures were very low, to negative 200 C or so. Which, because they were so low, the particles in those outside edges were probably covered by frozen water, frozen CO2, methane, and ammonia. So the formation of the sun marked the end of the period of contraction, and thus the end of the period of gravitational heating. With this lowering of temperatures, because again, no longer heating from the gravitational aspect of it, so there was no longer high temperatures near the sun, the particles with high melting points began to coalesce or join together. Okay? Coalesce means to join together. So elements such as iron, nickel, silicon, calcium, magnesium, sodium, and a few other ones started to form these metallic clumps, which started orbiting the sun. Again, because most of these elements were laying initially so close to the sun that once the temperature started to lower near the sun, those particles started to coalesce or join together. Okay? That's important. So these constant collisions caused the masses to coalesce into even larger bodies. So these elements, again, started making kind of clumps, and these clumps started to kind of collide against each other, and eventually making each clump getting to a larger clump and a larger clump, just gathering mass and gathering mass. So eventually making the four inner and rocky planets of our solar system. So those clumps started building up so much that the inner four planets of our solar system, those being Mercury, Venus, Earth, and Mars, started to form. And any remaining clumps that were outside of those four larger bodies, we now call meteors, because they're outside of the planets, but still within our solar system. And they're made up of basically the same elements that our rocky planets started to be made up and are still made out of basically today. So then temperatures rose as more material coalesced within each of these rocky planets. And due to high temperature and weak gravitational fields, the rocky planets were unable to accumulate lighter elements such as hydrogen and helium. So these hydrogen and helium elements were actually added by solar wind, not by the formation of the Earth itself, but rather later were kind of intaken, if you would, by solar wind. So at the same time that these rocky planets were being formed by the collision and the coalescence of the elements that were a little bit heavier, the outer planets were being formed as well. So the low temperatures that were on the outside of that disk meant that high accumulation of ices, such as water ice, if you would, such as ice, CO2 ice, methane, and ammonia ice, made these outer, more gaseous planet. So for the most part, again, they are made out of these ices, but there's some rocky and metallic debris as well. So this accumulation of ices accounts in part for the large size and also the low density of these outer planets that we have. Again, those being Jupiter, Saturn, Neptune, and Uranus. Gone through the formation of our solar system, we're going to go in a little bit in depth into the formation of the Earth and its very early history. So in Earth's very early history, the temperatures, as I had said before, were very high in the inner rocky planets. So it caused everything to basically melt, and by that melting, it made things within that big clump very homogeneous. So no change in composition. It was just a large mixture of all of the elements together. Again, those elements being iron, nickel, calcium, sodium, silicon, oxygen, amongst a few other ones. Okay? Eventually, the melting produced these liquid blobs of dense metal that sank towards the center of the planet, causing the current iron-rich dense core of the Earth. So, again, those liquid blobs of very dense metal, which were mostly iron and nickel, sank towards the center of the planet. Okay? The other effects from these early period of heating resulted in another process which we call chemical differentiation, where buoyant chunks of molten rock, which was what like the primitive crust, it rose up to the surface. So more buoyant things, less dense things rose up to the surface of that gigantic body that was initially homogeneous, now is starting to split chemically. So these more buoyant chunks were composed of mostly oxygen and elements seeking oxygen for molecule formation, such as silicon, calcium, aluminum, sodium, potassium, magnesium, and little bits of iron, the iron that was remaining that didn't sink to the core. And lastly, some heavy metals, such as gold, lead, and uranium, which have low melting points or were highly soluble in the ascending molten masses that were coming up to the surface, were scavenged from Earth's interior and concentrating in that developing crust. So those heavy metals that should have, been dense enough because of their low melting points were highly soluble and ascended along with those buoyant chunks of the primitive crust. So from this early differentiation period, we go to the main three subdivisions of the Earth's interior: the primitive crust that I just talked about, the iron-rich core that were again mostly for iron and nickel, and then that were very dense, and then the mantle, which is by far the largest layer and is located in between the crust and the core. So that's going to be that red area that you're seeing here in the top picture. So how continental crust formed and differentiated from oceanic crust is still under questioning, but currently from the oldest rocks that have been found in the Northwest Territories in Canada, we know that it must have happened at least 4 billion years ago that we had that differentiation between continental and oceanic crust. Another important consequence of this chemical differentiation process were the large amount of gases that were released and allowed to escape from the Earth's interior. So with all this movement and reworking of the initially homogeneous matter that we had within the Earth, there were some gases that also escaped from the interior and were able to make up the current atmosphere. So imagine the gases that are released today in volcanic eruptions. That was kind of the same process, or that's what we believe was the same process that created the proto-atmosphere. And then later, as the Earth continued to develop, the specific gas amounts that the atmosphere has now, it changed throughout.